Hello, my name is Dmitrii, and welcome back to a course on testing complex intelligent systems and autonomous vehicles. This is lecture number 7, titled Software Defects and Metrics. We're going to start with a discussion on how to evaluate testers and how much objectivity can be expected in this ambitious enterprise. Next, we will look at the concept of a metric and the criteria that a metric reflects, as well as what it measures, what metrics are and what they show, who needs them, and why. Then we will discuss quantitative metrics that tell us about the number of defects in the system under test. And finally, we are going to talk about the importance of metrics in decision making. A lot of ideas for this lecture were taken from Ken Kainer's and Walter Bond's article on metrics in software quality assessment. In addition, we can recommend other interesting articles. You can see some of them on this slide. Traditionally, I would like to refer you to the ISTQB certification programs, both foundational level and advanced level for test managers. And here are 64 essential testing metrics for measuring quality assurance success. The previous lectures raised interesting questions about the essence and the quality of testing. When we say something is good or bad, we're obviously giving it some qualitative assessment. When it comes to testing and product quality, this evaluation can present a dilemma when quality needs to be quantified. We have something we can count, because the purpose of testing is to find bugs. Defects are logged in bug tracking system and can easily be counted. If you find many bugs, then you do a good job. If a lot of bugs get fixed, it means that we have a quality product. But is it also straightforward? And what is many bugs exactly? Is it a universal notion? Is it the only indicator we have? Plus, we remember the testing principles from lecture 4, and one of them states that the absence of defects is not an indicator of quality. So it does not matter how many bugs you found if a user is not satisfied with the system. And here's one more point. When we try to rate something as good or bad, there can be difficulties. James Buck mentioned several possible problems. The notion of goodness is subjective and relies on feelings and demands a context. We need to know who evaluates what and under what conditions, since it can be highly subjective. And finally, sharing your assessment can lead to failure. Can we tell the truth about the poor quality of a product if we know that this will cause the project to be shut down and our team to be out of a job? As we can see, things are really complicated, because sometimes such nuanced and creative work needs to be evaluated, and that's where a variety of metrics come into play. In general, metrics are scientific concepts related to the desire to represent some qualitative feature more objectively. For example, mass helps us objectively evaluate a rather subjective concept of something being heavy or light. A measure of length, the concepts of long and short, or high and low. Same goes for volume, temperature, and speed. The concept of a metric relies on the concepts of measurement. Measurement is the process of assigning a number or category to an entity to describe an attribute of that entity. The definition given in 1946 by Stanley Smith Stevens adds that measurement is the assignment of numbers to objects or events according to the rule. By the way, Stanley Smith Stevens is an American psychologist and the author of famous classification of measurement scales. He identified and described such types as nominal, ordinal, interval, and ratio scales. So if measurement is a process of transforming qualitative attributes into quantitative indicators, then a metric is a measure which sets a rule on how to get a numeric value of some property or attribute. If we define a metric more formally as it is done in the IEEE standard, then it is a function whose inputs are software data and whose output is a single numerical value that can be interpreted as a degree to which software processes are given attribute that affects its quality. Again, the notion of measurability and metrics is a general scientific concept that has been used in our everyday life as well as in professional fields. Our task today is to look at how metrics are used in testing. The first question is whether testers need metrics at all. If they don't, then who needs metrics in relation to the testing process? In the ISTQB foundation level syllabus, metrics appear in several chapters. The ISTQB advanced level test manager syllabus has a whole section devoted to metrics. If you're looking for expert opinions, you will find that they talk about metrics in connection with the task of project management, rather than with testing in general. In particular, Degtyarenko mentions metrics specifically in the context of a manager's information needs. It has already been mentioned in the lecture 4 of this course that testing is an information service. Metrics is a form of presenting information about quality to project stakeholders. So, what metrics can such information be based on? Measurements can be qualitative and quantitative. Managers and stakeholders expect qualitative assessments but demand evidence in the form of quantitative measurements. Degtyarenko points out that all quantitative data is based on the qualitative judgments. For example, there is a task of evaluating how a tester or a team of testers is performing. This is qualitative information. We want to understand how skilled the team is, how effectively people are performing their tasks, and how reliable their results are. You can assess this in different ways. You can count bugs detected by employees. You can enhance the metric by considering the severity of bugs. You can also count how many bugs a particular person or a team finds per unit of time. Counting bugs is not always a clearly deterministic procedure. Some bugs are so hard to find, for example, memory leaks or timing errors, that a simple test scenario is usually not enough. They can be found only during several iterations of complex testing. That's why representatives of the context-driven school of testing suggest adding a qualitative method of evaluation to quantitative metrics for objective understanding. Degtyarenko gives an example of testers' work evaluation. In it, he suggests selecting some aspect, for example, defect reporting, and looking at the reports themselves. Are they clear and concise? Do they describe the problem exhaustively enough? Do they immediately show what the defect is? Can it be reproduced according to the description? Are there any unnecessary opinions? And what is the general tone of reports? If you process several bugs reports from one specialist, you can get an idea of the quality of his or her work and then rate it on the ordinal scale by assigning it a certain rank. For example, the tester is excellent at writing test scenarios and planning their implementation, but only satisfactory in describing problems in bug reports. Michael Bolton's opinion is somewhat close to that as well. He insists that it's more important to look at every bug report than to describe all the bugs in a project as a single entity. So, we're clear on the fact that metrics can be qualitative and quantitative, but it's also important that these metrics really serve the informational function and really capture the essence of the aspect they qualify. To make the evaluation process objective, you need good metrics. Good by itself, again, is a qualitative notion. It's a little easier when we deal with quantitative metrics. Here, the question about the value of a measurement boils down to the questions of validity and reliability. A measurement is valid to the extent that it provides a trustworthy description of the attribute being measured. A more detailed list is suggested in the IEEE standard for developing a metrics methodology, which names 6 criteria suggested to validate metrics. 1. Correlation. The metric should be linearly related to the quality factor as measured by the statistical correlation between the metric and the corresponding quality factor. 2. Consistency. The function of metric m itself must be monotonic. This rule must be followed for all values. If the quality factor variables are in the relationship f1 is greater than f2 is greater than f3, then the corresponding function values will also relate to each other as y1 is greater than y2 is greater than y3. 3. Tracking. When the quality factor changes from f1 to f2 in real time, then the function value should also promptly change from y1 to y2. 4. Predictability. If we know the value of the function y at some point of time, we can predict the value of the quality factor f. 5. Discriminative power. A metric shall be able to discriminate between high-quality software components and low-quality software components. Indicator values that are associated with high quality should be significantly higher or lower than those associated with low quality. The percentage of good test coverage should be significantly higher than the percentage of poor coverage. 6. Reliability. The metric must demonstrate all the aforementioned properties at least by a certain percentage of the metric application. When applied to qualitative metrics, validity criteria are proposed to be extrapolated as credibility ones. What allows us to evaluate the tester's work as something credible? The first aspect in relation to credibility is a sufficient level of knowledge and skills to work with certain tasks and data. It is very important to assess whether there is no bias or intention to please stakeholders at the cost of diminishing the importance of defects. Another aspect is transferability. It's how applicable the findings are to other data and conditions. Next is dependability. It's the methodological validity of the work, the systematic approach, the presence of necessary skills to solve the problem. And the last one is confirmability, a criterion very similar to reliability for quantitative metrics. It deals with assessing whether similar input data leads to similar results. That is, if we make some conclusion during the analysis of raw data and then give the same data to another person, then will he come to a similar conclusion? A special mention should be made of construct validity. The term refers to one of the most basic issues in validation. The question, how do you know that you are measuring what you think you're measuring? In the research paper on software metrics, Kainer and Bond give the following example. Suppose that while teaching a class, you use the following rule to assign grades to students. The closer the student sits to your lectern, the higher her grade. Students who sit front and center get A's. Those who hide in the far back fail. Intermediate students get grades proportional to the distance. Does this grading scheme describe a measurement? Kim Kainer and his colleague Walter Bond offer a whole system of evaluating metrics and illustrate the concept using defect count as a measure for quality of a tester and the status of a project as an example. The defects will be discussed a little bit later, but here we're interested in assessing the correctness and validity of the chosen metric. The first element of the framework is the answer to the question of what is the purpose of this measure. Example of purposes include: a metric can help assess your work and identify areas that need improvement. It can help assess the status of a project and check the progress. The purpose of a metric can also assess the team's performance. And finally, metrics can be used to inform project stakeholders, customers, or management about the product features, or it can be used to inform external stakeholders, regulators and authorities, etc. The higher the stakes associated with the measurement, the more important the validation. The next question is about the scope of a metric. Here we're looking for context. It can be specific methodology or just one specialist, one team project, team projects during the whole year, all projects in one organization for the last 10 years. As the scope broadens, the more confounding variables come into play, potentially impacting the metric. A metric that works well locally might fail globally. Next comes the question of the attribute we're measuring. We need to understand what is behind the measurement and what is the nature of the phenomenon we're describing with the metric. For example, to comprehend a temperature measurement, we need to have a good idea of the nature of hotness and coldness, in particular the heating and cooling behavior of various substances. There's a lot of controversy about measuring intelligence. Popular tests have been known to focus on one or few kinds of intelligence instead of encompassing them all at once. Metrics can be controversial, and that is understandable, given the complex nature of the phenomenon. The fourth validation factor is the measurement scale of a given attribute. It's important not to confuse it with the scale of the metric itself. For example, attributes such as length or weight can be measured on a ratio scale. We can tell if one object is longer or heavier than the other one. But if you take the field of mixed martial arts, the absolute weight of athletes is presented as a list of categories, for example, heavyweight, lightweight, etc. Next is the question of the natural variability of the attribute being measured. What are the intrinsic sources and degrees of variation of the attribute we're trying to measure? For example, a person's weight varies slightly from day to day. Another question of our framework is, what metrics do we choose? What is the function that assigns a value to an attribute? What metric do we use to measure it? The options may be counting, human or machine. For example, number of defects, time spent, number of branches, and lines in the code. Matching by a human or an algorithm or some other device. For example, a human can estimate the complexity of a product by comparing to one of several already finished ones. Comparison with the help of a person or an algorithm or some other device. For example, a human might say that one element of this specification is more clearly written than another. And finally, calculating time, using a computer, stopwatch, or some other external automated device, or by calculating the difference between two timestamps. For example, you can measure the time to a specified event, time to a first failure, for example, time between events, or the time needed to complete a task. This one is connected to the natural scale of the metric itself. That is, when we formalize a feature with a metric, the scales of an attribute and the metric can be different. For instance, the wavelength or the frequency, both ratio scales, and formalizing them with a nominal scale or a composite metric of HTML color coding, a set of scales that encode the intensity of each color component. What is the natural variability of reading from this measurement? This is normally studied in terms of measurement error. The next criterion is the question of conceptual validity. We discussed it earlier as a methodological basis for a metric. How do we know that this metric measures this attribute? Another way to ask this question is what links the attribute value to the metric value. If the attribute value increases by 20%, should we expect the measured value to increase as well? And by how much? The last question to answer within this framework is, what are the natural and foreseeable side effects of using this instrument? If we try to improve the outcome being measured, what effect will we have on this attribute? Kainer and Bond note that the flip side of metrics is that people are good at tailoring their behavior to things that they are measured against. Both Kainer and Bolton conclude that metrics are necessary as long as they help illustrate what is actually happening. Here is what Bolton said in one of his Twitter posts. But management wants numbers. I doubt that. Management most certainly wants to know things, and from testers. Knowledge about the status of the product and problems that threaten its value. Numbers might help to illustrate a story. They don't. Can't tell it. Only words can. In his paper on the quality of qualitative measurements, Kem Kainer goes on to say that qualitative measurements tell the story just the same. A skilled qualitative researcher relies on transparency in methods and data to tell persuasive stories. Decision makers rely on your stories to make important decisions. Let's go on. What metrics are used in software testing? Those who have sufficient experience know that there are a lot of them. The main question is, why? And this is very important. You shouldn't take up a metric just because it's trendy. It's necessary to understand why it's needed, what question it helps answer, and what aspect of work it describes. That is why it's the primary question in Kainer's and Bond's methodology. We would also like to recommend a Tricentis blog article about metrics. This one has a list of 64 metrics that help you measure and monitor test activities. The metrics are broken down into categories like fundamental metrics, derivative metrics, and so on. Everything is well organized and worth reading. Let's look at the groups of metrics proposed in the STQB Advanced Level Test Manager syllabus. 1. Project metrics, which measure progress towards established project exit criteria, such as percentage of test cases executed, passed, and failed. 2. Product metrics, which measure some attribute of the product, such as the extent to which it has been tested or defect density. 3. Process metrics, which measure the capability of the testing or development process, such as percentage of defects detected by testing. And 4. People metrics, which measure the capability of individuals or groups, such as implementation of test cases within a given schedule. The authors of the STQB syllabus encourage the use of metrics only after thorough analysis of the question, why? They say that effective use of metrics is possible only when you fully understand what they illustrate and why they do it. The metrics related to defects are perhaps the favorite ones in the field of testing. And even though there are people who give them a major role in evaluating the performance of testers, there are those who, on the contrary, believe that this metric is not necessary. Nevertheless, both actively speak out about metrics related to the number of defects. For example, Tom DeMarco, author of the essay Mad About Testing, says, "I can name only one metric that has value from now and forever, the number of defects." The opposing view is voiced by Michael Bolton and others from the context-driven school of testing. They say that a bug is not a problem. It's also an opportunity to learn some things. When you count instead of studying, you lose that opportunity. It's possible to make more extreme statements on the internet. For example, not everyone believes that defects should be tracked at all. Some statements are popular among experts in the field of Agile. For example, Lisa Crispin argues from the position of developers and speaks out against the defect tracking systems. Goiko Adzik calls defect tracking system a placebo, which gives a false sense of security about doing something by throwing digital coin into a wishing well, while hoping for better software. He goes on to say that fixing and tracking defects tells us as much about the product quality as humidity says about good weather. A frequent excuse for bug reports is that the bug measures signal quality in the software the same way humidity signals nice weather. There might be a 0 chance of rain, but that still doesn't mean that you will enjoy it if it's -10 outside. Let's move a bit away from metrics and to the question of how important defect information is. The context-driven testing school point of view on this was mentioned earlier. Such information is important both for learning new things and for qualitative assessment in testing. And one more thing, which is important in the context of this course, we have to keep track of information about defects recorded in AI systems. Such complex intelligent systems are inherently non-deterministic. Their defects can occur quite unexpectedly. Interestingly enough, there is already an attempt to create such a database, which is called AI Incidence. The creator of the database and the author of the research paper describing it hopes that the collected facts will help study the nature of dangerous failures in AI systems and possibly avoid serious consequences when they malfunction. Let's get back to the metrics. A good conclusion about them was made in Michael Bolton's blog. First of all, metrics should not be absolutized. They are not a direct and reliable representation of a product performance or testing. The irregularities extracted from the numbers are not always correct. There is an amusing site that illustrates this peculiarity of random correlations. On the next 2 slides, you can see some examples. These are truly random. Secondly, metrics are good for planning, but not for predicting. This is very important to understand that discrepancies with preliminary estimates should not be an excuse to punish people, not for meeting goals. Third, metrics should be used to test assumptions about the system rather than to dictate progress. A fourth consideration is that it's much more important to rely on personal observations, collaboration, and conversation with colleagues rather than reports. What matters is the game itself, not the final score. In addition, there is no point in counting unimportant and informative things and wasting time collecting and maintaining such metrics. Perhaps the most important point is that metrics are needed first and foremost to optimize work, not to present a product or process in a better light. Finally, it is important to understand that metrics are always only a small part of the answer to the question related to software quality. The main value lies in the more context-oriented, qualitative approach. That is all for today. Thank you for listening. Please think about what we discussed today and prepare your questions for the next Q&A session. Subscribe to this channel and help us get the word out about this course. See you soon.